This is the next video in a chapter on chemical bonding and molecular geometry. We have just finished talking about distortions from the perfect 120 and 109.5 and 90-degree angles in our geometries. And now we're going to talk about molecules that have more than one center. So we should be aware that molecules do get bigger than 7 atoms. It does happen. In fact, most atoms do. So we need to know what to do when we encounter one. And the way we're going to deal with it is we're going to say that each of the different central atoms in a large molecule has what we call a local geometry. And those local geometries contribute to a larger geometry for the entire molecule, which we are not ready to talk about that. See organic chemistry for more information. So let's give an example. Here is formaldehyde. Here is the Lewis structure for this molecule. And so we can see that there are several central atoms in this picture. Carbon is a central atom, and so is oxygen. 2 central atoms with the 4 hydrogens being the terminal atoms. So we can describe the geometry for each of the central atoms when we consider each of the different things that are attached. And so it'll help to draw the picture. So we can see that carbon is attached to 4 things: hydrogen, 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 and oxygen, which means that it should be drawn like a tetrahedral center, with 2 bonds in the plane of the page, 1 bond going back, and 1 bond going to the front. And then the oxygen also has 4 things attached. Don't forget to count the lone pairs. 2 lone pairs, a carbon and a hydrogen, are attached to that oxygen. So that means that the oxygen is also going to be in a tetrahedral environment. It's going to have a carbon, a hydrogen, and then we'll just draw on these lone pairs. So we can see them. We can label the geometry for each of these centers separately. So for the carbon center, we said electron geometry. It had 4 groups attached, 1, 2, 3, 4. So we called it tetrahedral, and we drew it as such. And then for the molecular geometry, we only count bonding pairs. All 4 of those electron groups were bonding pairs. So molecular geometry is also tetrahedral. For the oxygen, we said oxygen also was tetrahedral because it had 1, 2, 3, 4 electron groups. But its molecular geometry is going to be different from the carbon because 2 of those groups are lone pairs. And for lone pairs, we are going to name only the bonding pair shape, which we call bent. So that is all the information we need to know at this point about multicenter molecules. So now we know everything we need to know to do a problem complete from formula all the way to molecular geometry. So the process we're going to use for a problem like that is going to incorporate information from this lecture and from the last lecture. So the first thing you do when you see a molecule and you need the geometries, you draw the Lewis structure, right? We need the Lewis structure to tell us how many lone pairs and bonding pairs are attached to each atom so we can get to the geometry. So we draw the Lewis structure first, carefully. Then we count the number of electron groups around each of the central atoms, if there's more than one. And for each central atom, we label the electron group geometry, which loves all electron groups equally, lone pairs and bonding pairs. And then finally, we label the molecular geometry, which only loves bonding pairs and the atoms attached to them. And in the future, if you were to read another textbook or to move on to another class and someone was to say to you, what's the geometry of this molecule? They are looking for the molecular geometry, the geometry of the atoms only. We just need to find electron group geometry on our way to answering that question. So let's do a full example using that process for labeling and drawing the molecular geometry of this molecule, xenon tetrafluoride. So remember, when we find the Lewis structure, there was a whole separate set of steps just for that one. The first one was to count the number of valence electrons. So xenon is a noble gas. It lives in column 18. So it has 8 valence electrons. Fluorine is a halogen. There are 4 of them, and halogens all have 7 valence electrons. So 8 plus 28 should be 36 available valence electrons for this structure. So the next thing that we do is we want to draw the skeletal structure. We have to make a decision about which of these electrons is going to be central. And fluorine is a halogen, and it can only be a terminal atom because it is the most electronegative atom of anything in the table. So fluorine is never going to be a central atom. So we'll put xenon as the central atom, and we'll put the fluorines along the outside. And so the geometry of the Lewis structure, the positioning of the atoms isn't going to be perfectly accurate, but that's okay, because once we move to the actual geometry, then we will have an accurate shape. So we connect these with electron bonding pairs, 2, 4, 6, 8, because whatever this structure looks like, all the atoms have to be bonded together, or it is not in fact a molecule. So we subtract out 8 bonding pair electrons. So now we have 28 valence electrons left. The next thing we do is we complete the octets of the terminal atoms, which is fluorine. Each of the fluorines have 2 valence electrons that they share in this bond. So they need 6 more for a total of 8. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this math is not super well lined up, but that's just how it's going today. So there's 24 terminal lone pair electrons, which leaves 4 valence electrons left. And if we still have valence electrons left after filling the octets of the terminal atoms, we are forced to put those valence electrons on the center. And you can see that this xenon technically already has 8 electrons, but because xenon is bigger than phosphorus, it can take an expanded octet. So we can fill those last remaining electrons on the central lone pairs. Noble gases do not bond with things often, but when they do, they are no joke. So the final check to make sure we have a legal structure is to check the octet of each of the atoms. So for the fluorines, we've got 2, 4, 6 electrons belonging to them in lone pairs, and 2 more to make 8 electrons belonging to them from that bonding pair. So our fluorines are good. And for our xenon, we've got 2, 4, 6, 8, 10, 12. A very expanded octet for xenon. But it has at least 8, so we'll take it. And xenon is very large, so it is large enough to hold a few extra electrons. So satisfactory Lewis structure. The second step is to count the number of electron groups and to think about which type each of them is. So xenon is our central atom. That's the one we care about. So we're specifically labeling the electron groups on the xenon. We don't need to label the electron groups on the terminal atoms. So xenon has 1, 2, 3, 4, 5, 6 electron groups. Of those, 4 of them, the 4 that are attached to the fluorine, are going to be bonding groups. And 2 of them are going to be lone pairs. Those electrons that we stuck on at the end because we had nowhere else to put them. So 4 bonding pairs and 2 lone pairs. So we need to think about how we would classify such a structure. So any structure with 6 electron groups is going to be octahedral, according to our table. So we can stop there and go ahead and draw a slightly more accurate picture of xenon at the center of an octahedral structure, which already looks very different from the structure we did before. Then if we think about the molecular geometry, we know that two of those electron groups were lone pairs. And so we are only naming the shape that has 4 bonding pairs. And if we don't remember, we can always turn back to our table and look. Here's our octahedral 6 electron group. If we step over to 2 lone pairs, we get to the square planar structure. You can use the table for now as a crutch, but eventually we do need to have these names memorized. So 4 bonding groups in a 6 electron group structure is called square planar. And we remember that when we add electron lone pairs, they need to be as far away from each other as possible. So we're always going to add them across from each other, 180 degrees apart. So it doesn't matter which axis you put the 2 lone pairs on. I'm just going to choose this pair because it makes the picture look nice. And we'll add our 4 fluorines in the last remaining set. Here is our equator around the middle. That's the square planar part. This is the square plane. We'll add a note about these. Remember to add the lone pairs across from each other, because lone pairs need the most possible personal space. So when the question says label and draw the geometry, the label part is this. They want to know that the molecular geometry is square planar. The draw part is this. It's more than just a Lewis structure. It's a structure that shows the depth these bonds coming out of and going into the page, and specifically indicating where the lone pairs are placed and how far away from each other they are. So we now have all the skills we need to use a Lewis structure to determine what the molecular geometry looks like and what it is called for any of these small molecules. So the last topic we need to talk about is dipoles and polarity.